not exactly necessary. It's fine if we don't talk about it. So we are starting a little unit on probability and sort of where it comes from. So this is kind of going to be a sort of fast here. I have to turn this around. Sorry, it's backwards. I don't know how that happened, but okay, here we go. All right, so we want to be able to organize a tree diagram. Tree diagrams are sort of the foundation of probability, and then figure out the possible outcomes of an event for simple probabilities. So when we talk about probability, there's usually some sort of experiment involved, and an experiment is an action or trial with varying results. An action or trial with varying results. And so maybe an action that we're doing is rolling a die. So that could be an experiment. R-O-L-L-I-G, rolling a die. And of course, I'm talking about a standard die that you might use on a board game or playing poker or something like that. Oh, you don't use a die when you play poker. Craps, sorry. Yahtzee, yeah. All right. So, yeah, any sort of board game that has a die in it. And so an outcome is a possible result from your experiment. It is a possible outcome, a possible result. So if we roll a die, what's a possible result we could get?
5.
Rolling a 5, rolling a 2, rolling a 3. These are all possible outcomes, all right? And then we call the sample space, it's the set of all possible outcomes. And to know the sample set, the set of all possible outcomes, the set of all possible outcomes is what we need in order to be able to calculate probabilities. So the sample space, we use a set notation here, uses curly brackets. What is the set of all possible outcomes?
1, 2, 3, 4, 5, 6. Yeah,
that's right. 1, 2, 3, 4, 5, and 6. And that is the set of all the possible outcomes. And another way that we can figure out possible outcomes is by making a tree diagram. This one was really, really simple. But sometimes we do more than one action, more than one experiment at a time. And so when we have a bunch of different experiments that we're doing, then we can use a tree diagram to help us find the sample space when there's multiple actions. So we're going to draw a tree diagram for the situation here. So we have, we're going to pick a digit 1 through 8. So maybe we have a spinner that has you spin it, you flick it and spin it, it spins, right? Maybe it can land on 1 through 8, okay? And so that's the first action here. So what could we land on if we spin 1 through 8?
1 through 8.
Yeah, so we could land on a 1, we could land on a 2, we could land on a 3, a 4, a 5, a 6, a 7, or an 8. And so this is the first action. These are the possible outcomes. And then after we do that, then we're going to toss a coin. So we got a regular coin, and we flip the coin, and what could happen when we flip a coin? Heads or tails. So what might have happened is maybe we landed on a 1, and then we flip a coin, and we can get heads or tails. We could have had a 2, and then we flip the coin and get heads or tails. And so here what we're doing is creating this diagram that lists all of the potential outcomes, all the possibilities that could happen. So from each number, we then flip a coin, and then we could get heads or tails. And so what might happen, the sample space, when we actually think about what are all the possible things that are going on here? Well, the sample space is, well, we could have gotten a 1 and then a heads. 1 and then a head. We could have gotten a 1 and then tails. We could have gotten a 2 with a head. and then a 2 followed by tails. So what we're doing is we're listing how the outcomes might have happened. Does that make sense to you? Okay. And so continue. What else do we get?
3 heads, 3 tails.
3 heads, 3 tails. Good. 4 heads, 4 tails. 5 heads, 5 tails. 6 heads, 6 tails. 7 heads, 7 tails, and then 8 heads, 8 tails. All right? Which means there's a lot of different things that could happen. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes. They're all different. 16 possible different outcomes. Wowza. That seems like a lot of work. Does it seem like a lot of work? Okay. Well, let's turn the page. 16 possible outcomes. All right. Boy, maybe we're going to choose a day of the week and then choose a letter from the word math. I'm going to make a tree diagram for that. Well, let's see. Well, first I got to choose a day of the week. What are our possibilities there?
Monday through Sunday.
Monday through Sunday. So I'm going to start with Sunday, and I'm going to make it SU because I don't want to confuse myself with Saturday. Sunday, Monday, Tuesday, Wednesday. Oh, you know what? I need more space here. Sunday, Monday, Tuesday, Wednesday. Oh, Thursday, I'm going to do TH for Thursday. Friday and Saturday, SA. Okay. All right, Saturday. All right, so those are all the days of the week. And then after that, I'm going to choose a letter from the word math. So imagine I had M-A-T-H. What's up there, Paxton?
I have a question.
Yeah.
Can you take, like, the number of days you use 7 and just times it by the possible outcomes? So, like, if there's 4 letters in math, 7 times 4, 28 outcomes.
Interesting. Do we think that might be accurate? Possibly. Does it? Well, let's see what's going on. Let's make sure this is a good hypothesis here. So we had 7 days of the week, and we're choosing one of 4 letters. All right, well, if we got Sunday, then yeah, it could have been M-A-T-H. And then if I chose Monday, again, then I would choose a letter, M-A-T or H. Tuesday, we draw a letter, M-A-T or H. Interesting. Are we getting there? M-A-T or H. Yeah, this is like 4, 4, 4, 4. We're going to have a 4 for each one of these letters, aren't we? Right? Is that going to get us to 28? Yeah, it sure is. Ladies and gentlemen, congratulations. You have just learned the fundamental theorem, fundamental counting principle, sorry. The fundamental counting principle, so we could list all of these out, but man, it's exhausting. And sure, it works. It works great, actually, really great. And we could list our sample space, Sunday with an M, Sunday with an A, Sunday with a T, and Sunday with an H, and on and on and on. But it's exhausting, all right? And so the faster way to do it is when we have a couple of outcomes, when we have more than one outcome, we can use the fundamental counting principle, which is this. This is the fundamental counting principle. We can draw a tree diagram, but it takes forever, all right? So we don't want to do that. So instead, to find, God bless you, the total number of outcomes, if one activity can occur in M ways and another activity can occur in N ways, then both activities occur in M times N ways. We just have to multiply our possibilities together. All right? We can always make a tree diagram if we want to. If you're ever stuck, it's a good place to start and maybe remind yourself. But here we go. Let's try some more that are a little easier here. Let's see. Choosing a month of the year and then a digit 1 through 9. So we have 2 actions we're doing. So how many months are there?
12.
And then a digit 1 through 9, how many choices are there?
9.
All right. And so all we have to do is multiply, which is 108. All right, we're choosing a letter from the alphabet and then tossing a coin. We have 2 actions, and all we have to do is multiply them together. So how many letters are there in the alphabet? 26. And how many keys are on the piano? Don't know that.
108.
88.
We just had that in chemistry for one of our. We did like a Jeopardy thing. Team Jeopardy.
Yeah, just random factoids. All right. Tossing a coin. What can happen when we toss a coin? 2 outcomes, heads or tails. So 2 outcomes. 26 times 2 is 52. Good. Okay, choosing a pair of pants, a shirt, and a belt. You've got 3 choices to make. A pair of pants. Well, how many pants do we have? 3. We got 3 to choose from. Yeah, 3 choices for a pair of pants. What about a shirt? 5 shirts to choose from and 2 belts. So that's going to be 10 times 3, which is 30. Rolling a die. This is tricky. We're rolling the die 4 times. How many actions are there?
4.
4 actions that I'm doing. I'm rolling the die once, twice, 3, 4 times. So 1, 2, 3, 4 actions. So my little blank space here is the action. Yeah, and 6 each time. Rolling a die, 6 outcomes, 6 outcomes, 6 possibilities, and 6 possibilities, which is 6 to the 4th, which is 1296. Okay. All right, choosing 1 student from a class of 32 students. So I've got 1 class, and then I'm choosing from another class. So I have 2 outcomes here. How many choices do I have from the first class? 32, and from the second class? 27. 32 times 27 is? 864. Thank you. Spinning the spinner to the left 3 times. So we have how many actions? 3 actions. 1, 2, 3. And there are, when we spin this spinner here, what are the things that we can land on? 1 through 16. So we have 16, 16, and 16 for those possible outcomes. 16 cubed is 4096. 4096. All right, tossing a coin 5 times. Once again, reading carefully. How many actions are we doing? 5 actions. 1, 2, 3, 4, 5. And we're tossing a coin. What are the outcomes? 2 times 2 times 2 times 2 times 2, which is 2 to the 5th, or 32. And then down there, number 11, creating a 4-digit password from the digits 0 through 9. How many actions are there? 4. We have to push 4 buttons in our 4-digit passcode. That's 4 actions. 1, 2, 3, 4 actions. How many digits are in there from 0 to 9? 10. Very good. There's 1 through 9, which is 9, plus 0, which makes it 10 digits. All right. So this is 10 to the 4th, or 10,000, a 1 with 4 zeros. All right. Questions on any of those? All right. I like this stuff. I love the counting principle. I think it's so fun. Okay. This is really easy. But there we go. Okay. So probability. What's my time? 14? Okay. That's good. So probability has to combine all of those possible outcomes and figure out the chance of getting a winner. All right? And so probability is a measure of the chance that a specific event will occur. Not every event, but one that we want. All right? And so when all the outcomes are equally likely, the theoretical probability of an event E is the ratio of favorable outcomes to the total number of outcomes. And that's what this says. We use this notation, P of E. This is the probability of a certain event. All right, usually we specify like a red card on a standard deck of cards, something like probability of getting a red or probability of getting a blue. Probability of some event happening is what we want, which I typically call winners. All right, the thing that we're looking for, we want to win. So what do we want? What are the winners? Over the total possible outcomes, which is what we just figured out when we did a bunch of multiplying, okay? Probabilities have values between 0 and 1 and can be expressed as a fraction, decimal, or percent, so you are going to have to read carefully on Delta Math. So let's look. The spinner below is spun one time. Find the probability as a fraction in simplest form, a decimal, and a percent. So we have here, this says we want the probability that we're going to land on a multiple of 3. All right. So a multiple of 3. What are the multiples of 3 if we spin the spinner? 3, 6, 9, 12, and 15. Okay. You'll notice that I'm circling the winners. All right. So a multiple of 3 would be what we would call a winner, or what we want. That's a favorable outcome. So how many winners are there? 5. 1, 2, 3, 4, 5. So that's a winner. So that's 5. Out of how many possible places could we land on? 16. So 5 out of 16. That's our simplified fraction. You can see 5 out of 16 doesn't reduce. We can math frac it. It doesn't reduce. But as a decimal, 5 out of 16 is just 0.3125. So that's the decimal. You'll notice it's a number between 0 and 1. All right. How do we convert it to a percent? Move the decimal, but it's really because we're multiplying by 100. So times by 100, we get 31.25%, making sure you have that percent symbol on there. All right. So the blue color is a multiple of 3. What's the probability we get a prime number? Ooh, what are the prime numbers? 2. 5. 3 is also prime. What makes a prime number? Other than itself and 1. So it has factors of itself and 1 only. So 2 is 2 times 1, 3 is 3 times 1. 1 is not, because its factors are 1 and 1. It doesn't have itself and a 1. Like the and is the key there. It has to be something and 1. 5, 7, 11 was right. 15 is 5 times 3, 16 is 8 times 2, and 4 times 4. It's got lots of possibilities there. So there we go. There are our primes in red. So how many winners are there? 1, 2, 3, 4, 5, 6. Yeah. 6 out of 16. Is that a reduced fraction? No, it is not. We're going to divide by 2, so we get 3 out of 8. So there's our reduced fraction, and 3 out of 8 is the decimal, 0.375, and what's the percent? 37.5%. And again, you can get that by multiplying by 100 pretty easily. All right. Should you ever get a percent more than 100? No. No. That'd be bigger than 1, so that wouldn't work. Okay. Okay. What about the probability, of an even number or a number greater than 5? So what we're going to do is I'm going to mark all the winners. So first I'm going to mark all the even numbers. Well, how many are even? 8, 2, 4, 6, 8, 10, 12, 14, and 16. Those are all winners. Those are all even. What about ones that are greater than 5? What does greater than 5 mean? anything greater than 5. So 6 works, 7, 9, 11, 13, and 15. So everything I've marked with an orange line are all winners. That's a lot. That's pretty good odds there. Okay. So how many winners are there? 1, 2, 3, 4, 5. Yeah, very good. So I like how you just was subtracted because it's easier to take away 1, 2, 3. Okay. So 13 out of 16, that is reduced. I love that you subtracted. That's great. 13 out of 16 is 0.8125 times by 100, 81.25%. Okay, very good. Any questions on those? All right, let's look. Well, actually, I need to do D as well. Or means it could be either or. All right, it could be a number that's even, it could be a number that's greater than 5, and we combine them and get a bigger, lots of possibilities, okay? But and is a very different word in math, okay? And means it has to be both. So and means it has to be an odd number at the most 9. So can it be bigger than 9? No. Okay, so it has to be odd, and at most, at its highest, it has to be 9. So here we have a 1. What else is a winner? 3, a 5, a 7, and a 9. So those are all odd, and at the most is 9. Those are our only winners. It's not all the odds and at most 9. Does that make sense to you? Okay. So, and in this case, it must be both things. All right. And that's really important in math language. The and means it has to do for both. All right. Both has to be true. Okay. So this is 1, 2, 3, 4, 5 out of 16, which is reduced. That gives us a decimal of 0.3125 or 31.25% again. All right. I love these kinds of questions. Write as a fraction in simplest form. A pencil box contains, I'm just going to draw this out. It contains 5 red, 1, 2, 3, 4, 5, 12 blue. Oh man, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 blue, 10 green, 1, 2, 3, 4, 5. This is really ridiculous. 6, 7, 8, 9, 10 green, and 3 yellow. 1, 2, 3. Okay. So here's my box. It's got all the colors in there. If a marker is chosen at random, what's the probability that it is not yellow? Okay. So how many are in here total? 30 total. We always need a total amount, so we know that there's 30 to start. And how many of them are not yellow? 27 are not yellow. We just subtracted the 3 yellow out. That's very good. That reduces. I can divide by 3, so 9/10. That is our simplified fraction. All right. I'm just gonna stop right there, turn the page. So that's kind of a great question. We're gonna skip down here to complement of an event. The complement of an event is the probability that the event not occurring. Sort of what we just did. Since the sum of all probabilities in a sample space is 1, the probability of event not occurring is the probability of not E. This little symbol, that little tilde in math, is the word not. So the probability of the event not happening is 1 minus the probability of the event. Now, it turns out that I can use this formula if I want to, but it's actually a lot easier just to think about it a little bit. So here we go. The probability that it will rain tomorrow is 11 out of 15. 11 chances will rain out of 15. So what's the probability that it will not rain? There you go, 4 out of 15. Now, why does that work? Well, we can check the math here. So if I know the probability that it will rain, I'm going to write this down. The probability of rain is 11 out of 15. So the probability that it'll not rain should be 1 minus 11 out of 15. 1 minus the probability the event actually happens. All right, well, we need a common denominator. What's the common denominator of these two fractions? 15. So this 1 is the same as 15 out of 15. That's 1, right? And what is 15 fifteenths minus 11 fifteenths? 4 fifteenths. So do you want to do all that math? Or understand that 11 times it's going to rain. That means the 4 is not going to rain. All right? It makes total sense, right? All right. Let's look at number 9. A number from 1 to 30 is selected at random. What is the probability of not selecting a multiple of 4? This one's going to be a little harder to figure out. So I'm going to start by finding the probability of a multiple of 4. So first of all, in the numbers 1 through 30, what are all the multiples of 4? 4, 8, 12, 16, 20, 24, and 28. 1, 2, 3, 4, 5, 6, 7. All right, so there are 7 winners. 7 out of 30 is the probability of getting a multiple of 4. So what's the probability of not getting a multiple of 4? 23. Yeah, we got 7 that are multiples of 4. The rest are all going to be not multiples of 4, which there are 23 other possibilities. All right, so there's our 23 out of 30. All right, let's go to experimental really fast and we're done. So what we were talking about now, everything we've been doing is just theoretical probability. What we want out of the total possibilities. All right, that's theoretical possibility. What do we want out of what's possible? That's it. So, but experimental probability is based on the results of an actual experiment. So what did you do? Well, in this, we spun the spinner to the right 50 times. Red, orange, purple, yellow, or green was what our spinner had on it. And so for 50 times, we spun this spinner, and we did tick marks for how many times it landed on red, how many times it landed on orange, okay? Theoretically, landing on a, who knows what, or theoretically, it would have been 1 out of 1, 2, 3, 4, 5, all right? But we landed on red 5 out of 50 times. So find the theoretical and experimental probability if the spinner is spun again. So the experimental probability is just based on what happened actually, all right? So what's the probability of getting an orange experimentally? Yeah, 12 out of 50, all right? What's the probability of getting red or green experimentally? Yeah, how'd you get 15?
Well, red is 5, green is 10.
Yeah, so, or we just get to add them together, so 5 plus 10 would be 15 out of 50 trials. And, what's the probability it was not purple?
43 out of 50.
Yeah, how'd you get 43?
Adding all up, etc.
Yeah, everything but purple. 5 plus 12 plus 16 plus 10. All right, so experimental probability is really, really easy. All right, it just uses actual data. Theoretically, we just look at the picture. What's the probability I land on an orange? 1 out of 1, 2, 3, 4, 5. 1 out of 5. That's it. Just look at the picture. What should it be if everything was equal? What's the probability of landing on a red or a green space? 2 out of 5. All right. And what's the probability of landing on not purple? 4 out of 5. All right. So super easy. Theoretical, look at the picture. Experimental, look at the data. All right, questions? All right. Cool. A little long.